In the world of quantum computing, we are opening amazing possibilities that go beyond the limits of traditional computing. At the heart of this innovative journey lies the superconducting transmon Qubit, powered by a special component called the Josephson junction. But to understand the potential of this technology, we first need to explore the challenges hidden within it, especially the surface loss effects related to wiring in Josephson junctions. Chapter 1: Into the world of superconducting transmon Qubits. We live in a world of bits, where all digital information is represented by zeros and ones. The binary world is being transformed by the emergence of quantum computing, which uses qubits instead of bits. Qubits can be in a state of 0 and 1 at the same time, thanks to the principle of quantum superposition. It is like a coin spinning in the air, holding the potential to land on heads or tails simultaneously. When you add in the phenomenon of quantum entanglement, qubits can share information and act as one, making quantum computing potentially much faster at solving complex problems than traditional computing. Superconductors play a vital role in making quantum computing a reality. Superconductors are materials that have zero electrical resistance below a certain temperature. This amazing property is essential for maintaining quantum states and processing information. By using superconductors, qubits can maintain their quantum states without interference from the external environment. Transmon qubits are a prime example of leveraging superconductor technology. They are made by placing a Josephson junction between two superconductor pads. This junction, a very thin insulator between two superconductors, is crucial for storing and processing quantum information through quantum tunneling. Transmon qubits are popular for their stability and plain design among the diverse types of qubits being researched. These superconducting transmon qubits have the following features. Quantum superposition transmon qubits can be in states of 0 and 1 simultaneously, enabling complex calculations to be performed at once. Quantum entanglement: it is possible to entangle two or more qubits, allowing quantum computers to have much greater computational power than traditional computers. Unique tunability: transmon qubits can be adjusted externally through electrical or magnetic signals, allowing for precise manipulation of quantum states. However, superconducting transmon qubit technology is still evolving and faces many challenges. One of the main challenges is precisely controlling interactions between qubits and maintaining the stability of their states. Research is ongoing in optimizing Josephson junction design, reducing surface loss and suppressing noise. Additionally, various technical advancements are being made to overcome the constraints of operating qubits at extremely low temperatures. Recent research has uncovered that surface loss in the wiring of Josephson junction devices in superconducting transmon qubits is a major factor, limiting qubit performance. To address this issue, researchers are looking for ways to optimize wiring designed to reduce surface loss and improve the quality factor of, for instance, by widening the wiring or changing its structure. Qubit performance can be enhanced. This journey into the world of superconducting transmon qubits is just beginning. Where we go and what discoveries await us are still unknown. But an amazing world is unfolding before us. Chapter 2: The challenge of Josephson junctions and wiring. In the realm of quantum computing, we are unlocking incredible possibilities that go beyond the limits of traditional computing. At the heart of this innovative journey are superconducting transmon qubits, which operate through a special component known as the Josephson junction. However, to truly grasp the potential of this technology, we must first explore the challenges hidden within, especially the surface loss effects in wiring related to the Josephson junctions. Simply put, a Josephson junction is a structure made of two superconductors, separated by a very thin insulator. This setup plays a crucial role in quantum computing by controlling the state of qubits. Through Josephson junctions, we enable qubits to be in a quantum superposition state, a core functionality of quantum computing. However, this remarkable capability comes to life when the Josephson junction is connected to superconducting pads via wiring. This is where we encounter one of the challenges that limit qubit performance: surface loss. Surface loss refers to the unnecessary dissipation of electromagnetic energy on the surface of the wiring. This loss can significantly degrade the efficiency and reliability of qubits, particularly if the wiring connecting the Josephson junctions is not properly designed. It can shorten the qubit's relaxation time, i.e., the time a qubit can maintain quantum information. So how can we minimize this surface loss? The answer lies in optimizing the wiring design. Research shows that adjusting the width and shape of the wiring can significantly reduce surface loss. For instance, widening the wiring or changing the material composing the wiring can help control the distribution of electromagnetic fields, thereby reducing loss. Optimizing wiring design goes beyond mere technical details. It is essential for realizing the ultimate potential of quantum computing. With optimized wiring, we can extend the relaxation time of qubits, allowing quantum computers to perform more complex calculations. This opens quantum computing to bring innovations in various fields such as medicine, cryptography, and material science. By overcoming the challenges in Josephson junctions and wiring, we take another step towards a bright future of quantum computing. Chapter 3: The Future of Superconducting Qubits. Challenges to overcome and potential to unleash. In the fascinating world of quantum computing, superconducting transmon qubits are getting a lot of attention. This technology offers keys to solving problems that were previously out of reach, pushing beyond the limits of modern computing. However, with the advancement of this technology, we face several challenges. One crucial factor determining the performance of superconducting transmon qubits is surface loss. Recent studies have shown that surface loss in the wiring connecting qubits is a major limiting factor for qubit performance. Good news is that by optimizing the wiring design, we can significantly reduce this loss and improve the quality of qubits. This progress is crucial for the advancement of quantum computing technology. A deep understanding of wiring design and its optimization is key to creating higher performance qubits. According to recent research reported in Nature, reducing surface loss in wiring can improve qubit performance by up to 20%. This research contributes significantly in the following ways. It uses finite element simulation and experimental analysis to confirm that a huge portion of qubit surface loss originates from wiring connected to the Josephson junction. It demonstrates experimentally that optimizing wiring design can notably improve the qubit quality factor by up to 20%. Compared to previous studies that focused on improving the capacitor, pad design, or the Josephson junction itself, this research highlights the overlooked contribution of Josephson junction wiring to overall surface loss. The innovation of this research lies in focusing on wiring, a component of qubit design, identifying wiring as a significant source of dielectric loss, and successfully demonstrating quality factor improvement through wiring. Optimization presents a new method to enhance the performance of superconducting qubits. This research not only advances our understanding of factors affecting qubit efficiency, but also proposes practical design adjustments for future quantum computing advancements. This will speed up quantum algorithms and reduce error rates, further enhancing the practicality of quantum computing. Quantum computing is an incredibly interesting field on its own, but it also holds the potential to revolutionize various aspects of our lives, from cryptography and drug discovery to climate change research. Specifically, improvements in the performance of superconducting transmon qubits will play a key role in making the possibilities of quantum computing in these application areas a reality. Of course, there are still challenges ahead for the development of superconducting transmon qubits and quantum computing technology. We need research to reduce error rates and increase computational power, including addressing surface loss in wiring. However, these challenges also offer us new opportunities for research and innovation. Through the continuous development of superconducting transmon qubit technology, we can accelerate the implementation of quantum computing. Today, we introduced recent research showing that optimizing the wiring design of widely used superconducting transmon qubits can enhance quantum computing performance by up to 20%. Thank you for watching Science Catch by Sam.